All right, guys, so this is our second Flip the Classroom lesson for Chapter 6. And in this lesson, we are going to talk about an alternate way of defining a point's position on the plane. So normally when we define a point's position on the plane, we use the Cartesian coordinate system, which defines a point's position on the xy axis with its horizontal and vertical distance from the origin, right? So right here, we might travel some distance a out on the x-axis horizontally and some distance b on the y-axis vertically, and that x value of a and that y value of b would come together to give us our ordered pair AB, which would define the point's position on the plane. Now right here, we also call ordered pairs of x and y values rectangular coordinates. And the reason for that is that if we take the horizontal and vertical lengths that are defining these points' position with respect to the origin, they create a rectangle between that point and the origin. So another word for an ordered pair with x and y values would be rectangular coordinates. Now, as we're defining our point's position with horizontal and vertical lengths, it's worth it for us to take a second and say, is this the most natural way we would describe a point's position on the plane? Right here, generally we want a point of perspective, right? And we're going to basically say, from that point of perspective, where is this other point? Is it the most natural thing to define a point's position with a horizontal and vertical distance? If we were to describe traveling from the origin to our point AB, is it the most natural thing to say, first I travel a horizontal distance over A units, and then I travel a vertical distance up B units? Right here, if we were describing traveling to the point, a more natural way of getting there might be to turn in the direction of that point, and maybe we would call that turn a rotation from standard position. So some rotation theta turns us in the direction of that point, and then we might travel a direct distance from the origin to that point, right? And maybe we call that direct distance r. Now what we've done in this case is we've defined our point's position as a distance from the origin in a direction theta. And this is what we would call a pair of polar coordinates. So right here we have rectangular coordinates AB, those are x and y values, and right here we have polar coordinates r theta, and those are going to be the polar coordinates that define that point's position on the plane. And what we're going to do today is talk about defining points with the polar coordinate system, which is a coordinate system where points are defined by distance from the origin r in a direction theta defined as a rotation from standard position. So right here we've got our plane sort of set up with slightly different units of measurement. Now we're going to be talking about direct distances of r and angles of theta, right? On our polar plane, we say that the pole is O, and that coincides with the origin, 0, 0, on the xy axis. We say that the polar axis coincides with the positive x-axis, and that's going to be the initial side for all of our angles of rotation from standard position, which will define the direction that our points are in. Right here we say that points on the polar plane are a length r in a direction theta. We say that r is the directed distance and theta is the directed angle. Right here we've got an example of a polar point, and we want to graph that point. So right here, if we come over to our polar plane, we can take a look at graphing this guy. Now before we graph him actually, we'd want to take note of the rotation increments we've got right here. Basically what we're seeing is our rotations broken up into increments of pi over 6 or 30 degrees. So the only stops we're missing to sort of that we would see on the unit circle are the half quadrant rotations of 45 degrees or pi over 4. So right here, first if we're going to plot this point, we would want to rotate theta in the direction of that point. So right here we're talking about a rotation of 2/3 pi, so that's a rotation all the way over into the first stop of our second coordinate, and then we would travel a distance of 3 in that direction. So we'd go out 3 units, and that defines our point's position with polar coordinates. So right here, the rotation that we've drawn and the distance of 3 are generally things we won't draw when we're plotting polar points. In general, we want to be able to do that in the end without sort of drawing this stuff out. But for right now, it's a good sort of visual aid for us. Okay, so let's talk about graphing some different kinds of polar coordinates. When we're graphing polar coordinates right here, we want to take note that the theta could be a positive or negative value. And basically right here that makes sense, because if we're rotating from standard position, we could be rotating up or down from the polar axis. But also, our R value could be positive or negative, right? And we're going to talk about what that means in a second when we graph our point B. So let's first graph our point A. Right here, we would say A is a distance of 1 in a direction of negative pi over 6. So we're going to rotate down negative pi over 6, and then go that distance of 1 in the direction of negative pi over 6. And that defines the position of our point A. We'll sort of draw this as A. Now, originally I just put this A and B to differentiate the points, but it's nice to sort of have that A there so that we can sort of see what point we're talking about. All right, so let's go ahead and erase our visual aids and graph B. So right here with B, we're looking at a rotation of 225 degrees, which is going to be a rotation that takes us 45 degrees past 180, so basically halfway into the third quadrant. Now right here, with a negative R value, what we're going to say is, instead of us traveling forwards 3 units, we're going to actually be traveling in the reverse direction, or the negative direction, with that negative R value. So right here, instead of us traveling forward 3 units into the third quadrant, we're actually going to be traveling backwards 3 units into the first quadrant. And that rotation with a negative distance of 3, or a distance backwards of 3, defines our point B. And so that would be our point B on the polar plane. So right here on the next page, we've got some polar coordinates to have you guys practice graphing. So why don't we go ahead and pause our video now and give these 3 polar coordinates a shot. So we'll go ahead and pause the video. All right, so these are our 3 points. And let's talk about the rotations and the R values that took us to these 3 points. So right here for A, we start out with a standard position rotation of 3/2 pi, so that's going to rotate us all the way around to that negative y-axis, and then we're traveling a positive 4 units in that direction. So basically what that means is us traveling forwards in that direction 4 units, and that takes us down to our point right there. If we're looking at B, we've got a rotation of 150 degrees, so that's going to be a rotation that's all but 30 degrees of 180. And now what we want to take note of is that our R value is a negative 2, so instead of us traveling forward 2 units, we're going to be traveling backwards into the fourth quadrant 2 units, and that takes us to our second point right there. Okay, so right here with C, we've got 3/8 pi, and what we want to take note of with 8/3 pi is that that's a rotation that's actually greater than 360 degrees, or 2 pi. It is greater than 1 full rotation. So we could basically think about this as the point 3 and then 2 2/3 pi, which is going to be a rotation all the way around, and then an additional 2/3 pi, which takes us to that first stop in the second quadrant. And now we'll travel a distance of 3 in that direction. So traveling a distance of 3 takes us out to our point right there. So now that we've had some practice graphing some points, let's go ahead and answer some questions about points on the polar plane. So right here, will each pair of polar coordinates define a unique point? So right here, what we're asking ourselves really is, if we've got a pair of polar coordinates, is there any way for this pair of polar coordinates to give us some other point? And what we would say is that we're only going to be able to evaluate our rotation and our R value in one way, right? So when we're asked if we're going to get a unique point from this pair of polar coordinates, we would have to say, yes, one rotation and one distance gives one point. So right here, each of these polar coordinates, and in fact, any pair of polar coordinates, or sort of ordered pair on the polar plane, is always going to define one point, right? So let's turn that question around. Will each point be defined by a unique pair of polar coordinates? So right here, is this point right here only going to be able to be defined by the pair of polar coordinates we have right here? And right here, what we would have to say is, well, we know that our R values can be positive or negative. So actually, if we have an R value of -4 and a rotation that takes us in the opposite direction, let's say pi over 2, if we plot that pair of polar coordinates, we would rotate to pi over 2. And now right here, from that rotation, we would then travel in the opposite direction 4 units, and that would take us down 4 on the y-axis, on the negative y-axis, to that same point. So right here, first off, we can say, no, negative r and a rotation in the opposite, I'm going to abbreviate opposite, direction gives the same point. So that's one way we could get that same point with a pair of polar coordinates. Right here, what we've seen with our point C is that we can have rotations greater than 360 degrees or greater than 2 pi. So now we've got the potential for coterminal angles. So right here, for an R value of 4, we could say a coterminal angle of, let's say, 7 over 2 pi is actually going to take us in the same direction as 3/2 pi. So this too would define basically that same point. That pair of polar coordinates would also define the point. So right here, we would say a rotation of 7/2 pi is a full rotation plus an additional rotation of 3/2 pi, taking us to that same direction. And then right here, we could go down 4 units, and right here, 4 units in that direction is going to take us to that same point. So also, right, also coterminal angles with the same R value give the same point. So right here, we basically talked about 2 different ways we can get polar coordinates to define the same point. Let's sort of talk about this in terms of a pair of polar coordinates r theta. So if we've got a pair of polar coordinates r theta defining a point, we could say that we would be able to get to that same point if we had the same r value and a coterminal angle. So right here we could say a coterminal angle to theta would be any theta that differs by a rotation of 2 pi, right? So we could say any increment of 2 pi plus theta is going to give us a coterminal angle. So we could call a coterminal angle 2 theta, theta plus 2 pi k, where k is an element of the integers. Similarly, we could say that, I'm going to try to bring this down a little bit. I need to move that all down. Similarly, we could say that if we had a negative r, a rotation in the opposite direction, which would differ by pi radians, would take us to the same point, and any coterminal angle to this angle with the negative r value would also take us to the same point. So we could say plus 2 pi k would also take us to the same point. Now right here, we have, if we can simplify this a little bit, we can say negative r, and then right here, theta plus, and then we could say 2k plus 1 pi is going to take us to that same point. Okay, so right here, what I want you guys to do is to go ahead and try to find 2 points, two pairs of polar coordinates that are going to define the same point right here as the pair of polar coordinates we've got. And I want one that has the same r value and one that has an opposite r value, right? So right here we would want a pair of polar coordinates with -2 that define our same point, and a pair of polar coordinates with a +2 that would define the same point, and the same thing with C. All right, so we're going to go ahead and pause the video and give this one a shot. All right, guys, so we've got some pairs of polar coordinates to talk about defining the point. So right here, if we've got -2, 510, 510 is a rotation of 360 degrees plus an additional 150. And that's going to take us to that same rotation. And with a -2, we would then go backwards to define that point. So that rotation and that distance r of -2 and 510 degrees will take us to the same point. If we had an r value of 2 and a rotation of 330, that would be all but 30 degrees of a full rotation. And then a distance of 2 in that direction also takes us to that same point. For C, right here, if we have a rotation of 2/3 pi, there's an easier rotation that is less than a full rotation. And now right here, that distance of 3 will take us right to that point. If we have a rotation of 5/3 pi, that's going to be all but 1/3 of a full rotation. And now right here, a distance of 3 in the opposite direction, right? So that -3 tells us we're going in the opposite direction, is also going to take us to that point. So right here we have, we talked about points on the polar plane. What we're going to do in the next video is talk about how to convert rectangular coordinates to polar coordinates and polar coordinates to rectangular coordinates to define the same point on the plane. All right, guys, so we'll stop the video here, and I'll see you in the next video.